We're going to determine whether a linear model is actually appropriate for a set of bivariate data. This is a formula we use for linear regression. We know that the slope is next to x, and the y-intercept is the constant. Below are the formulas that we use to find the slope and to find the y-intercept. So let's start with slope. The slope is the correlation coefficient r times the standard deviation of y divided by the standard deviation of x. The y-intercept is found by taking the slope times the average of all of the x values and then subtracting that from the mean of all the y values. These formulas are on the AP exam, except the difference is they use different notations. So instead of A and B, they use B0 and B1. So it looks like this on the formula sheet. What you have to remember is that the constant, which is the y-intercept, and the variable next to x is always going to be slope. So the number of miles in thousands for 11 used Hondas has a mean of 50.5 and a standard deviation of 19.3. The advertised prices of these pre-owned cars had a mean of 14,425 and a standard deviation of 1,899. The correlation coefficient for these variables is r equals negative 0.874, a negative strong correlation. Find the linear regression equation and interpret the slope and y-intercept. So before we can do any calculations, it's best to figure out which one's the explanatory variable and which one's the response variable. So the two variables being recorded are the number of miles on the car and the price of the car. So it makes the most sense to say that the miles driven on the car will probably affect the price of the car. So now that we've done that, we can go back to the problem and label the appropriate values. So 50.5 is the mean of the number of miles, so it's got to be x bar, and its corresponding standard deviation is 19.3. The mean of all of the prices is 14,425, and the corresponding standard deviation is 1,899. To find the slope of this relationship, we would do the correlation coefficient times the quotient of standard y, standard deviation x. So we substitute those values in, and we find out that the slope is negative 85.996. This makes sense because we saw that the correlation coefficient is negative, so that means that the points should be going down, and the slope confirms that because it's a negative slope. Now we can use the slope to find the y-intercept. Here's the formula for y-intercept. We take y bar and x bar along with the slope and substitute it. We find out that the y-intercept is a very large value, 18,767, which makes sense. If there were no miles driven on a pre-owned car, then you would purchase it for approximately $18,767. So this is called the line of best fit. If we sketched a graph through all the data points, this would be the closest line to it. The advertised price of the car decreases on average $85.99 for every 1,000 miles the car has driven. If the car had 0 miles on it, we would expect the advertised price to be about $18,767. We're going to find the linear regression equation using the formulas for the following data. So this time we actually have to input the data into the calculator. So in this case, year is probably the explanatory variable, so I put that in L1. Number of Americans over the 100 years old, I put into L2. And then I did second vars, stat, two variable statistics, and I found x bar, sx, y bar, s of y, and then I went and did a linear regression and found r equals. So using these values, take a moment and put them into the formulas to calculate the slope and the y-intercept for this linear regression. So hopefully for slope you got 6.06. The y-intercept is negative 12,038. So our linear regression model is if we predicted the number of Americans over 100, we would have this formula. So it's great that we can calculate the linear regression equation using these formulas, but if the data isn't linear at all, then these formulas don't help us. So one of our jobs as statisticians is determining whether or not a linear model is a best fit. So as you can see in this one, when you do a stat calc and Lagenreg, for L1, L2, we get the same slope and the same y-intercept as if we did the formulas. So again, sometimes it's hard to tell whether or not a form is actually linear. When the correlation is really weak, it's hard to determine whether we should say no correlation or whether we should say a weak correlation. So there are a couple ways we can check to make sure that the data is actually linear. The first thing we need to do is we can make something called a residual plot. The residual plot is the difference between an observed value of the response variable and the predicted variable. So for instance, it is the difference between your y value that you saw and the y value that you predicted. So the formula we use for residual is observed y minus predicted y. And we know those two variables are different. The observed y is the variable y, and our predicted y is y hat. So that formula shows you the residual. I always get confused about which one's actually first, so think of it alphabetically. Observed minus predicted. Kind of like when we were doing chi-squared, observed minus expected. So we have a scatter plot, and the red line depicts the linear regression equation. A residual is the vertical distance between the point that you actually got from your data and how far it is to your line of best fit. So that distance is called a residual. So we use residuals to determine whether or not the data is actually linear. So all of these lines all of these data points that are above the line of best fit, these would have positive residuals, and all of the points that are below the line of best fit would have negative residuals because they have a negative distance. They're underneath the line of best fit. The ones above are a positive because they're above the line of best fit. So what we do is we find the residuals for every y value, and then we plot them. So on the x-axis is the explanatory variable, and then on the y-axis you can see it's the residual. Notice how there's a green line at 0. All residual plots have a line at 0. If everything was perfect, then your residual would be 0, right? Your predicted and your observed would be the exact same thing. So all of our residual plots have a line in the middle at 0. Because that's the average. So what this tells us is that this observed value of this data point was 3 above the predicted value. It's a positive 3 residual. This one down here at -1 represents a value that was 1 below the predicted value. And like I said, the green line represents the mean of the residuals. The negative and positives, they should cancel each other out and make a sum of 0. That way the mean is always going to be 0 for all of them. Here's the key point. When you make a residual plot, we're looking for something that gives you no pattern. It kind of sounds counterintuitive, but if all of your residuals make a non-pattern graph, then the original data is approximately linear. So characteristics of a residual plot. It's a scatter plot with the x as our x-axis and the residual is our y-axis. If no pattern exists in a residual plot, we say that the form is approximately linear. The mean of the residuals is 0, so the line y equals 0 marks the mean of all of the residuals. So if you take a look at the first graph, this is a residual plot. So these are how far the data points were from the predicted data points. And you can see it's scattered all around that y equals 0 line. So that means that a linear model is appropriate. So our predictions, since they're equally spaced out, means that they're probably pretty close. But in the next one, you can see that as you get further out on the x-axis, that the data is getting further and further away from that y equals 0, which means that our observed values are not that close to the predicted values when we were doing later towards the the upper end of the x values, so this is probably not going to be a very good prediction. So we're looking for things that are not appropriate. So you can see in the first graph, it makes a distinctive curve. This is a residual plot. So this is the residuals of the original data, and when it makes a curve like that, this is not an appropriate model for a linear regression. Take the second one. It's also a curved line going down. That is not an appropriate data point, or not appropriate to use a linear regression for that set of data. The one on the bottom makes a linear residual plot. So you would think a linear plot would mean that your data is linear, but that is not the case. We were looking for something that's scattered all over the place. So this one is not a good match for a linear model. So let's practice making a residual plot. So if you grab your calculator, we're going to enter the year in L1 and the year in L2 if you haven't done so already. The next thing we're going to do is we're going to... So when I do stat calc and I choose 8 linear regression, this is the equation that we get. So this is how we're going to make a residual plot. I'm going to go over to L3 and I'm going to write down my predicted values. So the way we're going to do that is we're going to type in our line of best fit, but in the place of X, we're going to put L1. So we highlight L3, we type in the line of best fit, and instead of X, we're going to place L1 because that's where all of the explanatory variables are. These are the values you should get in L3. Next, we want to calculate the actual residuals. So remember, residuals are observed minus predicted. So our observed values are in L2. Our predicted values are in L3. So the next thing we're going to do is go all the way up to L4, highlight it, and type in L2, L3. These are the values that you should get for the residuals. So you can see that for 1994, our predicted value is 5 below the observed value. Now we're going to make a scatter plot, except we want to be really careful because the scatter plot we want to make is residual plots. So our explanatory variable is still going to be X, which is L1, but our response variable is going to be our residuals, which is in L4. This is our residual plot. So does this mean that our original data has a linear model? We'll take a look at the residual plots. It's a curve, and we said that curves, or anything that has a distinct shape, should not use a linear model for its for the modeling of it. So a linear model is not appropriate for this set of data. Take a moment and try the next one. See if you can sketch the residual plot in your calculator. So these are the values you should get. Those are your predicted values. We have to find the line of best fit first, and then instead of X, we would have to type in L1 in its place because that's where all of our X values are. Our residuals are observed minus predicted, so we do our L2 minus L3, and then when you plot it, you should get a graph that looks like this. Again, you can see a distinct curve, which means that a linear model is not appropriate for this data set. All right, try this one. Assuming the temperature is X and the ice cream sales is Y, determine if a linear model would be appropriate for this data set. Hopefully you get a graph like this. So you can see here there's no distinct shape or pattern in this residual plot. It's kind of all over the place. It's kind of equally scattered. So we would say, yeah, a linear model would be good. So we do want to use the line of best fit for this data. Another method we can use to determine whether a linear regression is appropriate is by finding something called the correlation of determination. The symbol we use for that is r squared. The symbol of correlation of determination is r squared. So if you actually wanted to find the correlation coefficient, all you would have to do is take the square root of the correlation of determination. But keep in mind the plus or minus is there because that depends on the direction of the data. If it was a positive association, we would do obviously positive r, but if it was a negative association, it would be negative r. So the correlation of determination reports how successful the regression was explaining the response. It's the likelihood of future events falling within the predicted outcomes. So the higher the coefficient, the higher the percentage of points the line passes through. If r squared is 0.8, then 80% of the points should fall within the regression line. So this is the sentence stem that we use when we're talking about correlation of determination. So it would say blank percent of the variation in blank is explained by the least squares regression line. So we would change r squared into a percentage, and this blank would be the response variable, whatever it is in context. So correlation coefficient is determination is a percentage of the variation in response variable that's explained by the least squares regression line. So let's say a study was conducted to investigate the relationship between age and blood alcohol concentration measured when convicted DWI jail inmates were first arrested. So we can see that this is the person's age and this is their blood alcohol content. We want to determine the correlation of determination. So we type this data into the calculator, we go to least squares regression line, and we'll find out that r squared is 0.113. This means that 11.3% of the variation in blood alcohol content can be explained by our least squares regression line. So you could say weight, how many drinks, things like that. So there are way other variables besides age that could be leading a change in the response. So this line of best fit does not work very well for this set of data. So even though there's a strong correlation between two variables, it does not prove causation. Remember, for example, a study on birthdays may show a large number of birthdays happen within a 2-month time frame. This does not mean that changes the seasons that cause pregnancy, that the change of seasons causes pregnancy. The only way that you can prove causation is through a randomized, controlled experiment. Just because two things are related does not mean that one causes the other. There are two major types of linear regression models that we could make. The first one is called a median line, and the second one is called a least squares regression line. The equation that we use in AP statistics is the least squares regression line. In next class, I would like to show you why it's called a least squares regression line.